choose for big data. Why, what, and how of big data, which actually I have cut out most of it. And then we go into the recent development in networking and their role in big data. It turns out that most of the stuff that we have discussed applies to big data as well. And so that is there. And then how big data can be used for networking as well is the last part, third part. So as you can see, the whole big data was enabled by networking. If the networking, the advances were not there, then you would not have virtualization. We have spent so much time on virtualization, and that virtualization made the cloud possible, and the cloud made the fast computing and the large storage possible. And as a result, now we can do big data. I mean, big data problems have been around for 10 to 15 years, but it was not possible for everybody to do these things. Now with the virtualization and the cloud, anybody can do big data, and that's why it has become so popular. Now, the next slide is MapReduce. We have already done it. I just wanted to remind that what we need to do for the way big data is done now is that we divide the work into many computers, and we want to make sure that the computers that are doing the work also have the data. So right on this slide, we show the people the computers that are doing the work, and we call them task agent, the task node. And on the next slide, we have the data node. The data node is where the data is. So one of the things that the Google said in their original paper, that we really need to keep the data local. We need to keep the data exactly where the compute nodes are. So even though it shows on this picture only the data nodes, but these are also the compute nodes. Okay, and if you want to do computation on, let's say, on B1, B2, or B3, you would just use the leftmost node here, shown because that is where the data is. And this is different from the previous way of arranging storage, where previously storage was a whole different rack. So in one rack they will have a storage. The whole rack in the data center will have a storage with the disk arrays, and then they will use the fiber channel to connect them to the another rack where they will have all the computers. So that is changed now. So basically what we have is local storage. All right, and so local computation. So even though we have two names here, data node and the task node. So next slide. The task tracker and the data node, they are same, one and the same. You see it says DN plus TT. DN plus TT means, you just really want DN and TT to be the same node. All right, and so how do you do that? And that is what is possible with networking now, which was not possible before. So there are 5 things that the big data needs in terms of networking. First, it needs to make sure that you can do the computation at the same place where the data is. So the code and the data co-location. Right? The second thing is that the network should be able to handle the big variability in the demand, because basically what happens is that when you have MapReduce, lots of map jobs get done at the same time, and suddenly there is a whole avalanche of data coming to the reduce processors, and so the network needs to be able to handle that kind of thing, right? Third is the fault and the error handling. So that is another thing, is that we keep the data on 3 different nodes, we keep the computation on 3 different nodes, and if anything fails, the job is still complete. Security. So that's another part. Actually, we haven't gotten into security and our networking issues, but with all the VLANs and other things, it's only authorized users can get the access to the data, other people cannot. Synchronization is the map jobs should be comparable. So that's another thing, is that when you divide the map, when you divide the jobs, you want to make sure that they all are similar, because if one job is very big and it takes a day to finish and the other jobs are very small and are finished in few hours, then the reduced jobs are just waiting, doing nothing. They cannot reduce really. I mean, they can reduce piece by piece, but it is much easier for them if they get all the pieces together. So how this is possible, right? I mean, I can finish some of these right here and then go through the other ones later on. First, code data location, actually, we will spend more time in the next few slides. But synchronization is very easy. Basically, what you do is, when you divide the jobs, if they are not equal, then you just give more processing capacity to the job that needs more processing capacity. I mean, basically, you don't have to run 10 VMs on every physical machine. You could run 2 on one, 3 on other, and 5 on the other one. And so what happens is that the more VMs are there, the less powerful that VM becomes. And therefore, when you have two controls here. You have the job size and you have the VM size. They can be both controlled so that the jobs finish almost simultaneously. Make sense? All right. So now we go to the next slide about the code and data co-location. Before actually I go to code, data, and location, let me just tell you what recently happened in networking. So first of all, the speeds went up. We have 100 gigabit right now, and the 400 and 1000 are being discussed in IEEE. And so that way, the access movement, the movement of data has become very easy. So even if the data was not local and you had to move it, that is possible today. Okay? So that is one thing, is the high speed has helped a lot. Second thing is the virtualization, and the next 4 or 5 slides on virtualization. So I will, go more detail later. And then there is software-defined networking and network function virtualization. Now these modules will be taught in more detail in the next part of this course, but I will give you just one slide summary today as part of this lecture. Virtualization. So 5 things have happened in virtualization. First, the computation has been virtualized. Storage has been virtualized. And then the rack storage connectivity, and I will explain all of these 5 things in the next few slides, but now you can have the rack storage so that it can appear local to any of the machines. And then the data center storage can appear local to any machine, and the metro and global storage can appear local to any machine, right? Because of the virtualization. So first, virtualizing computation. And this actually, again, it is a repeat for this particular class because we have discussed so much about virtualization. But the idea is that in the old days, when you moved the machine, they changed the subnet, and things were not easy to move. So you could not really move VMs very easy. And one of the things that made cloud computing possible is that now the VMs can be moved very easily. And so that is one thing, is that with Ethernet extending the whole data center, you don't have to worry about any change in the addresses, and therefore the VMs can move freely, and so the computation can be moved anywhere in the data center. Then second thing is that with the provider bridging and provider backbone bridging that we discussed, the Q and Q and MAC and MAC, the numbers of these machines can be handled as well. Previously, you could not handle millions of machines or millions of VLANs. Now, with those standards, the numbers we can handle really big cloud data centers. Any questions so far? This is all kind of repeat, but just a reminder. Virtualizing storage. So the first thing the networking people did to enable data center cloud computing is to get rid of the fiber channel. Remember, previously every computer needed to have 2 cards, one fiber channel card for storage and one Ethernet card for networking. And so basically IEEE worked hard to make sure that everything that the fiber channel gives can be gotten by the Ethernet. So all these new standards which came out just in the last 2-3 years basically made that possible. And you might remember that we discussed the priority-based flow control and enhanced transmission selection etc., how they make Ethernet now provide the same basically capabilities that fiber channel provides for storage. So fiber channel is going away, and this unified networking basically saves a lot, because now you don't need two cards; you can just have one card, and operator expenses as well, because the fiber channel is a very special field. Very few people know fiber channel, where Ethernet is basically everybody knows. Anyway, the next thing was to virtualize the rack storage connectivity. And now here comes the SRIOV. And I don't know whether some of you remember, but SRIOV is a single root IO virtualization, where you could have one PCI card, and it will create many PCIe cards, right? Virtual PCIe cards. And so here what I have shown is that there is a disk which is connected to the PCI card, and you can divide the disk into red and blue and other colors. And the red VM thinks that it is connected to a disk which is red color, and the blue disk and blue VM thinks that it has a blue PCI which is local. So you can see now that that any VM can make the disk, any part of the disk, local. So this is how the data node and the task nodes both basically can be on the same VM, because we can just by virtualizing properly move the data to the node that needs it. So the idea is that this SRIOV really helped create the second thing was the multi-root IOV, which actually made it even better. With multi-root IOV, you did not need the PCIe card on every machine. You just need a few PCIe cards in the rack, and therefore those parts of the rack will have some disk, and those disks can be now shared anywhere in the rack. All right. So now you can see the VM's reach, and this is all to make the data local. Make sense? That now any part of the disk you can say, well, this part of the disk belongs to this VM, and so on and so forth, and therefore you can easily adjust, the location of the data as well as the computation. And notice that no data was moved. That is the beauty of it, is that while we are changing the location of the data is not being moved. Okay? All right. And then if the data was not in the same rack, then Ethernet comes to help. Ethernet comes to help by the bridge port extension, where everything basically is within one hop, logical one hop. And so storage could be anywhere, and then it will appear local, although in this case, the data will move. Because if the disk is at the other end of the data center, and you are doing computation at some other end, the data will have to be moved, but at a very high speed and at basically less complexity of computation. The programming, etc., is all hidden. So this bridge port extension helps by making the whole everything connected to the same switch, same bridge. And then the same story can be said about the metro storage. If the storage in some other part of the city, in some other data center, we have these standards. Now I haven't discussed, I think, VXLAN, NVGRE, TRIL, etc. in this course, and I have actually the lectures on that. And someday we will come back to virtualization more. Right now we need to move on, but these are the standards which allow you to connect data centers. And with these standards which are being done in IETF, you can connect data centers which are located across the city, are located in different cities, and they will appear as one Ethernet. Okay, so your one Ethernet can extend the city, it can extend the country, and as we see in the next slide, it can extend the world. All right, so that is the next slide, virtualizing the global storage. And so this is already being done. Energy Sciences Network, ESNet, uses a virtual switch to connect members located all over the world. So they might have the disk located in Japan, USA, France, Germany, whatever countries. And what they do is they set up a virtual Ethernet switch. So everything appears like it is connected to one switch. And that basically makes the use very simple. Although in this case, I mean, the data has to move, and you need really high-speed worldwide networks. But the thing is, the use and the programming and other things are much easier, because if everything is local, then you don't have to worry about the details of how the data has to be moved from this location to that location. So in general, because of the virtualization, the networks have become what we call fluid. They're liquid, and you can shape them in any way you want, wherever you want. And as a result, the world, I mean, like they say, the world is flat, so the network has become flat, and you draw your own network. Everything is virtually local. So you can just draw what you want local, what you want remote. So, as opposed to previously, you had to worry about how things are connected, but that detail is now hidden from the user. Okay, right. So the question is, when you say draw means, can you design the network the way you want it? Yes. So all the virtualization stuff allows you to put the switches anywhere, right? Virtual switches. So you could say, well, I want the router between these two, and I don't want the router between these, and these has to be on the same network. And so any kind of things you can do, yeah, so you can do by orchestration, or you can do by, whatever way you want. But basically, you can have an overlay that looks exactly the way you want it. The underlay, the physical network is different, and you don't have to worry about that physical network connectivity. Software-defined networking, which is actually the next module we might get into later on. But today, I just want to tell you, because that also is relevant to this whole virtualization stuff, is that software-defined networking, what they did was they centralized the controllable in the control plane. So what is the control plane? Basically, all the routers and the switches, they have to prepare a forwarding table. And then once they have the forwarding table, they can forward the data. They can look at the destination address into the forwarding table, and we can call them routing table, and then forward. So the process of just looking at the table is called data plane, because that is has to be done at gigabits per second. And the process of making the table is called the control plane. That doesn't have to be very fast, although it requires lots of computation. Forwarding has to be done fast. It does not require any computation. It's just a table lookup. All right? So that is done in the hardware. The data plane is done in the hardware. The control plane is done on a processor, CPU. So generally, each router or a switch has a processor, which talks to the other CPUs, other routers and other switches, and then figures out what the shortest path to different places is. All that is control plane. Okay, so the control plane, they said we just need to not do it in every router, in every switch, and we can take all the control plane and put it into one computer. So that is the controller which gets the connectivity information from everybody, and then finds out what is the shortest path, makes a routing table for everyone, and makes routing tables for everyone, and sends it to them. All right, so there is a central controller which does all the routing table construction. And construction, and the switch, the what we call the switch, the switches, they just do the data plane. So because they don't need a very powerful CPU now, they can be cheaper. They don't need hardware for the control part. They just need the hardware for the forwarding part, data plane. They can be cheaper. All right. So that is one thing, is that software-defined networking gives you a centralized control plane. The second thing it gives you is programmability. Now that the control plane is in one computer, you can put any policies you want, and you can change the policy any minute you want to change it, and it goes to all the computers at the same time, all the switches at the same time. You see, previously to change the policy, you will have to talk to each one of them one by one, and then they will have to kind of exchange the messages with everybody else, with their neighbors, and see if they have the same policies, and then find the path. It was a very slow process. Now with the SDN, everything is in one place, and so you can prepare all the tables right away and then send it to them. Okay, so we have programmable control plane. And now as a result of that, because now we have programmable control plane, we can orchestrate. Orchestrate means you can change thousands of the switches at the same time. So I have shown here the picture of an orchestrator, the director. When they move in the orchestra, when they move, the director moves the stick, everybody's tune changes right away, right? So that is what is done in networking now, is that the central controller, when it says something, the whole provisioning, you can provision thousands of machines, thousands of switches very fast. That is called orchestration. And so large Hadoop topologies can be created on demand. So you can just decide right away that, okay, I need 1,000 maps task nodes. I need 200 data nodes, whatever, 1,000 data nodes, and that you can do very fast with software-defined networking. Well, SDN, okay, first of all, the cloud is data center. And SDN can easily handle a data center. And what it can do is it can divide a data center into multiple virtual data centers. So basically, that is what you can do. It can make a data center multi-tenant. And what will happen is then you can say, well, these switches belong to tenant 1 and these switches belong to tenant 2. And the central controller can accordingly change the routing so that nobody's packets go onto somebody else's network. They are not visible. So yes, SDN makes it possible to create an overlay of any kind you want on a network. You are saying the nodes in the control plane. All right, there are no nodes in the control plane. Actually, there is only one controller. Everything is in the data plane. But some nodes are shown in blue, some are shown in red. And so basically what these are is that some of them understand SDN, which are shown in blue, and some of them don't understand SDN, and they're shown in red. Okay? So the red ones work as before. They will have to talk to their neighbors and find their routes. But the ones that are blue can talk to the controller and find their routes. All right, so these switches, these are actually more like routers and switches, not computers. So the blue things and the red things, all the dots here are only they could be V switches inside a machine, but these are switches, let's say, okay? So some of the switches are physical and some of them might be virtual. So even the virtual switches can be controlled by the controller, and they can get their forwarding table from the controller. Okay? Okay, all right. If there are any other questions, please feel free to interrupt, okay? Now, so the last thing. is network function virtualization. Again, we are going to have a bigger lecture on NFV. But what is happening is that people realize that they can do a lot in software. So they said, why do we need any special hardware? So there is a group in ETSI, actually, European Standards Institute. Telecommunication, ETSI is European Telecommunication Standards Institute, where they have started work on NFV, not network function virtualization. And what they're saying is, let's divide the functions that we do inside the networking devices, and we can just implement them in software on a standard processor, a standard, let's say, Intel processor. And then we can combine these functions modules to get anything we want to make. So, for example, there could be a module for DSCP, there could be a module for NAT, there could be a module for forwarding, there could be a module for QoS, and each of these are programs that have a predefined interface. So if the interface is standard, then you could buy DSCP from one vendor, you could buy the NAT from another vendor, and you could buy QoS from another vendor, and put them in your PC and make a router out of it, right? And all of these functions could be VMs, actually, virtual machines. And so, if one function doesn't work, it doesn't affect the other functions, and so on. And so they're defining the interfaces for these modules. And once this is done, then what will happen is we will have app market similar to the iPhone app market. Once the iPhone people defined their API and then said anybody can write the application. So now in future, anybody can write their DSCP module, somebody else can write their NAT module, somebody else can write QoS modules. So there will be hundreds of NAT modules available on the market for $199 each. And the prices will go down significantly now because it becomes a distributed market. Right now it is all basically one supplier market. If you buy a NAT from one company, say Cisco, you have to buy the DSCP from Cisco, and you have to buy the router from Cisco, everything from one company. But then with basically this network function virtualization, you could just get the apps from different places and combine them. And by these modules, obviously, there will be lots of applications which will provide privacy and security as well. So, for example, in this picture, I have shown NAT, but you could have firewall module, you could have intrusion detection module, you could have SSL offload module. Whatever you need, you could just buy an app and put it there. All right. So the last slide is about networking has enabled big data, but now one of the consumers of big data is networking, because the networking itself has become a big data problem. Now, previously in the data center, we used to have few thousands of machines. Now we have tens of thousands to hundreds of thousands of machines, physical machines, and then 10 times that number of virtual machines is going into millions. That many switches, routers, NICs, and everything has to be basically arranged. When you see the traffic pattern, you get a very big matrix, right? And we have to be able to figure that out quickly as to where the faults are. We have to predict where the congestion is going to happen or where the congestion is. All this has already become a big data problem. And so all the techniques of big data, such as Hadoop, etc., are being used to manage the data, manage the cloud itself. All right? Big data analytics, for example, when you do prediction, you can predict where the failures are going to happen before they happen. Same thing you can do here. Okay? So now that big data has become feasible and easy, obviously the cloud people are not only providing the service to other customers, but they are using it themselves as well. All right, so summary. The summary is that I/O virtualization allows all storage in the rack to appear local to any VM in that rack, solve the co-location problem of MapReduce. So we saw how, without moving any data, the data becomes local to any VM in the rack by using MRIOV. That was the first thing, right? Second thing is with network virtualization, the storage anywhere in the data center or in the other data centers or other part of the world can appear local. Now, in this case, it is just appears local, but it is really, so the data has to be moved. So we want to avoid that for large amount of data, but sometimes you need to do it, and you can do it. Third message was that the software-defined networking allows orchestration. Now, this is the word that you have to know from now on. Orchestration of a large number of resources. That means you can provision, you can start a large number of switches, virtual switches, routers, and you can then manage them, monitor them, orchestration, right, of large number. And you can create dynamically create Hadoop clusters. And then network function virtualization will allow these clusters to have special functions and security in the multi-tenant cloud. So now what will happen is, now you don't need any special hardware. You can just use the standard processors as networking devices as well. So previously you needed switches, etc. Now you can just use the processors as the switches. All right. Any question about this module? Because this is probably the last module on big data. We will have to move on to the software-defined networking next time. Any question about anything in the big data? All right. So in this, we have shown you two nodes, name node and data node. You understand these two functions. Data node keeps the data, and the name node keeps track of where the data is. You understand? All right. So the name node is the master for the data, and the data node is the slave for the data. Basically, so there are thousands of data nodes, maybe hundreds or tens or whatever number of large number of data nodes, and then there is a master name node. Okay. Now the same thing needs to be done for the jobs, for the compute. We need a master and we need lots of slaves. Okay. The master is called job tracker, and the slaves are called task tracker. So there are thousands of task trackers and one job tracker. Job tracker knows who is up, who is down, who is working on what. Okay. So now we have two masters. We have job tracker, which is one master for compute, and we have a name node, which is the master for data location. And we have two sets of slaves. One is the data node, which have the data, and we have task trackers. So the name task tracker is kind of confusing. It looks like task tracker is tracking something. You could have called them task node. Then it would be much easier to understand. They're just doing the job. They're not tracking anything. They're doing the job. So they're the compute jobs. And now we need both the task and the data to the same place. So in this picture, we have shown DN plus TT. DN is the data node, and TT is the task tracker. All right, so we have four kinds of node. Let's just do one more time. Job tracker. What does job tracker do? First of all, is it a master or a slave? You have to answer. That's the question. Yeah, master for compute. Now name node. What is name? Is it master or a slave? For data. Right. And now we understand. So what is the data node? Yeah, a slave for the data. And so there are hundreds of those. And then task tracker is the slave for the slave for the job tracker, but it's doing the job. It's really doing the task. It's not tracking anything. Okay?